All right, well, welcome back. So in the previous lesson, we started to have a look at the differential equations chapter, where we basically had a look at two different concepts of differential equations, where the first one being the linear or the separable differential equations. So if we have a differential equation of this form, we could solve it by using separable. So they're going to be called separable differential equations because you could separate a function of two variables into two separate functions that are going to be independent from each other. Uh, and then, so we looked at how the method would actually work. So you would have to write this into differential form so that we would have all the x's on one side, all the y's on the other side. And then we would have to integrate this, and then we would have a solution for that. So that was one of the differential equations that we had to look at. So we had to look at a couple of examples of how to solve differential equations that are separable. And we also had to look at some other concepts involving initial value problems. Um, so that's basically if you have an initial condition given, then you would just have to find what the constant value is, and that would just be an extra step just so that you could find the exact solution to the differential equation. And another thing that we also had to look at was the linear differential equation. So basically, if we had a differential equation of this form over here, we're able to solve this differential equation by finding the integrating factor, which we call mu of x, where mu of x, we actually found it to be the exponential function here. So that is our integrating factor. And then, well, once we found the integrating factor, we just substitute it back into this equation, which is the solution. And basically, you would just get this result, which is called your solution of your differential equation. So remember that this formula, you could also memorize it if you would like to, but that is up to you. So, and then we also had to look at some other examples involving linear differential equations. So we would just go ahead and use this formula directly. And so that's about it for this lesson, that previous lessons as a recap. So we had to look at a couple more examples, and now let's go ahead and start with the new stuff, which the first thing that we'll talk about is called the reduction of order. Now, let's say that we had a differential equation of this form. So we have ay double prime, by prime plus cy equal to 0, where a, b, and c are all functions of x. And so if we divide both sides by a, what we would get is that, well, y double prime plus b divided by ay prime plus c divided by ay. This is equal to 0 then. Now, if we let p be b divided by a and q be c divided by a, then what we would get is that, well, y double prime plus py prime plus qy is equal to 0. So why are we having this kind of differential equation of this form? Well, the truth is, well, this will come down later on. So we're going to be assuming that y equals to uy1 is going to be a solution of the differential equation. So whenever we're solving any kind of reduction of order problem, we always have to assume that one of the functions is a solution to the differential equation. But it's going to be completely valid that it's going to be one of the solutions. But our goal here is that, well, if we could find one solution of the differential equation, are we able to find a second solution of the differential equation? So that is the purpose of the reduction of order. If you have one solution, you can find the other solution. That is the purpose. So once again, if y is equal to uy1 is a solution of the differential equation, so let's find y prime first. So y prime, by the product rule, this is simply just going to be uy1, u prime y1 plus uy1 prime. So that's for y prime. And for y double prime then, that means we would just have, well, u double prime y1 plus u prime y1 prime plus u prime y1 prime plus uy1 prime double prime. And so simplifying this, what we would actually get is u double prime y1 plus 2u1 or u prime, should just be u prime, y1 prime, and then plus uy1 double prime. Okay, so we found y prime and y double prime. So let's go ahead and substitute this back into the differential equation that we had put out here. So that means if we put this in, we would get, well, the py squared, or y double prime, I'll denote it by using red. The y prime I'll denote with blue, and the y, I will denote this by green. So for the first thing is that we have the y double prime up here. So if we put that in, what we would get is that, well, u double prime times y 1 plus 2u prime y1 prime plus uy1 double prime. Okay, and then if we have the p out here, so we have the plus p next, and we would have the blue solution next. So this one would be u prime y1 plus uy1 prime. So that's for the p. And as for the q one, then the q, and then we multiply it by uy1. So this would be uy1. Now here's the thing. We could actually common factor out a couple of terms here. Well, let's see why. Well, we have a term uy1 double prime. We also have uy1 prime and this p out here. And we also have a q and a uy1. All right. So from here, what we could do is common factor that. So let's go ahead. We're common factoring out the u and see that, well, we actually have y1 double prime plus py1 prime plus qy1. Now, what did we say about y here? We said that, well, if y1 is a solution to the differential equation, or if this is a solution, then that means it must equal to 0. Aha, so this term is of the differential equation form that we had originally. This is actually going to equal to 0. Interesting. Okay, and then what we just have is just the other terms. So this is just going to be plus u double prime y1 plus 2y1 prime plus py1 u prime. This is equal to 0. Now let's make a substitution. Let's say that, well, w is u prime. Then the above equation that we just created, so it's just going to be these two terms here, is now going to be linear and separable. So let's see what we get here. So if we rewrite this as y1 u double prime plus 2y1 prime plus py1 u prime equal to 0, then substituting this in, what we have is y1 w prime plus 2y1 prime plus py1 w equal to 0. And what is this exactly? Well, this is exactly a linear differential equation, but in terms of y now. So here, our y is going to be a function of x. So here, we could actually solve this by linear differential equations. So if we divide both sides by y, so what we get is w prime plus 2y1 prime py1 divided by y1. And this is multiplied by w equal to 0 using the differential equation formula that we had talked about in the previous lesson. So we have a differential equation of this form over here. In this case, our q of x is going to be equal to 0, right? Okay. So that means, well, since p here, our p is going to be this 2y1 prime plus py1 divided by y1, and our q of x is equal to 0. Then that means our integrating factor is going to be mu of x, which is going to be e to the power of negative of the integral p, so 2y1 prime, plus py1 divided by y1, and this is going to be dx here. Okay, so that means our differential equation, well, maybe it's not wise to solve this linearly, but so let's try to do it using another way. So let us go ahead and use put this into differential form. So maybe that will be easier because this form is not one that you would want to work with that well. So let's write this into differential form. So note that since we have y w prime, this could also be written as dw. So I'm taking this entire thing, I'm rewriting it as a differential form. So what I have is dw divided by w, and this is plus 2 y1 prime divided by y1. And I will also have a plus p dx. This is equal to 0, or all this here should equal to 0, right? So now if we solve this, what we would actually need to obtain then here is going to be this form. So we have ln of wy1 squared. This is equal to the negative integral of p dx plus c. And so that means wy1 squared is c1e to the power negative px dx. So that means, well, since w is equal to u prime, and if we rearrange for w, solve for w is equal to c1 e to the power negative integral px dx divided by y1 squared. And since we have u prime then, is equal to what we had up here, so c1 e negative integral px dx divided by y1 squared. Then integrating this again, u is equal to c1 times the integral of e to the power negative px dx divided by y1 squared dx, plus a c2 out here as well. Now, if we let c1 equal to 1 and c2 equal to 0, so that's a typo over here, should be c1 equal to 1, then the second solution then will actually be given by y2, which is equal to y1 integral of e negative px dx divided by y1 squared. dx. Okay, so that's good. We found the formula for the reduction of order. So this is called the reduction of order. So let's have a look at some examples here. So remember that when we have to assume that we have to assume a solution is a solution of the differential equation. Our goal here is to find the second solution. So if y1, which is x squared, is the solution of the differential equation given by x squared y double prime minus 3x y prime plus 4y equal to 0, let's use the reduction of order formula to find the second solution. So remember that the reduction of order formula, it only works whenever we have this form. So let's go ahead and rewrite this into the form that we would want. So that means dividing both sides by x squared. So that means y double prime minus 3 divided by x, y prime, 4 divided by x squared, y equal to 0. So now, remember that our px is the only thing that we would want here. So this thing here. And that comes from this p over here, which is the one that is attached to the y prime. And in our case, the y prime is attached to negative 3 divided by x. So that means, so p x is equal to negative 3 divided by x. So using the reduction of order, you have y2 equal to x squared times the integral of e negative integral of negative 3 divided by x dx divided by x to the 4th power, because remember x squared and then a square, so we have to put it as a 4th dx. Now this is equal to x squared. If you do the integral of the e, then you would get e to the power 3 ln of x divided by x to the 4 dx. Then this would equal to x squared integral of x cubed x to the 4 dx. So this would just be the integral of 1 over x. And so that is just going to be equal to x squared ln of x, where we'll assume that x is greater than 0. So that is going to be the second solution. So therefore, y2 equal to x squared ln x is a second solution. Good. All right. So let's have a look at some more examples that uses the reduction of order formula. So what we have is y1 is equal to e to the power 2x, which is going to be the solution of this differential equation here. What we want is to find the second solution to this one. All right. So what we would have here, we have it in standard form already. So that means our p is just going to be this negative 4 here. So p is equal to negative 4. So that means, well, y2, which is equal to e to the power 2x, which is the first solution, times the integral of the negative p, so that's going to be negative 4 dx, dx, divided by e to the power 4x, because e to the power 2x and then square that thing, we'll get e to the power 4x dx, e to the power 2x. If you integrate, you get e4x, e to the power 4x, so that becomes a 1 then. So integral of 1 is just going to be x. So that means x e to the power 2x is the second solution of the differential equation. So let's have a look at the third example. we have y1 is equal to cos of 4x, which is a solution of y double prime plus 16y equal to 0. So let's use the reduction of order to find a second solution. Now here, we don't actually have a y prime here. So our y prime term is missing. Well, that's also the same as saying 0 y prime. Maybe it's just not included here. So that means we would have to assume that our px is going to be equal to 0. So that means by the reduction of order formula, you have y2 equal to cos 4x times the integral of e to the power negative 0 dx divided by e to the power, or no, cos squared of 4x dx. So that's going to be cos of 4x times the integral of e to the power c, so it's just going to be a constant then, divided by cos squared of 4x dx. So I'm going to bring out the e to the power of c, rewrite the 1 divided by cos squared as secant. So what I have is e to the power c cos 4x integral secant squared 4x. And this one, we should know what this integral is. It's e to the power c divided by 4 cos of 4x. So I brought out the constant. And this is going to be tan of 4x. Now I'm going to let a be this value here. So let this be a. Now this here will just turn out to be sine 4x because tan is sine over cos. Cos cancels, and we're just going to be left with the sine of 4x. So therefore, the second solution is going to be given by a sine 4x. So let's have a look at one more example. So similar to the previous example, we have a y prime that is missing. So that means we would assume that our p of x is equal to 0. So that means we do the same thing. So y2 is equal to cos of x times the integral of e to the power c. So skipping the integral because that's just going to be a constant value, say sometime. Cos squared of x dx. So that's ec cos of x sec squared of x dx. And then, so if we compute the same thing again, so this integral here is just going to be tan of x. And tan of x is sinh of x divided by cos of x. So the cos's will cancel. We'll just get a, which is equal to e to the power c, sinh of x. So I'll leave the last one as an exercise for you to try on your own. And it's fairly similar to the ones that we had a look at before, especially to this one over here. It's pretty similar. Okay, so with the reduction of order formula, we're now ready to have a look at the next concept, which is called the homogeneous equation. So if we have a differential equation of this form over here, then we call this equation that we have a homogeneous equation of degree n. All right. So in particular, our study in this case will be focusing on second order differential equations here. So let us consider a differential equation of this form here. So say we have ay double prime plus by prime and cyx equal to 0. So where a, b, and c are constants. So we try to find a solution of the form y is equal to e to the power mx. So that means our y prime here has to be equal to memx. And our y double prime is m squared e mx. Right? So let's make this substitution here. Well, we see that if we have am squared emx plus bm emx plus cemx equal to, so we're going to actually common factor out a couple of terms here. We're common factor out the emx, and emx. So that means what we have is am squared plus bm plus c emx equal to 0. Now it's important to note that if we want to solve this equation for m here, our e to the power mx will always have no solution. So e mx cannot equal to 0 for all m. So that means our solution is going to be based on this quadratic here, our am squared plus bm plus c. The equation that we have attained, so this am squared plus bm plus c, is actually called our auxiliary equation of the differential equation. So if we try to solve for this differential equation, we would see that, well, m is actually going to be equal to the quadratic formula. So we have b plus or minus b squared, or ac, whole thing square rooted, divided by 2a. So that means we'll have two solutions of the differential equation given. So from here, there are three separate cases that we have to consider because of the discriminant that we would have to check out. So let's say that alpha 1 and alpha 2 are distinct real roots, where m is equal to alpha 1 and m is equal to alpha 2. Those are your two solutions of this differential equation or auxiliary equation. So that means the solution of the differential equation is given by these two roots. So we would be given for each one. So we would have C1 E alpha 1x plus C2 E alpha 2x. That's your solution to the differential equation if they're going to be distinct real roots. So yeah. And they're going to be real as well. So now let's say that, well, if alpha 1 and alpha 2 are real, but equal roots, then that means here what we'll have is that, well, alpha 1 is equal to alpha 2. But what that means by the discriminant is that the b squared minus 4ac is going to equal to 0. So that means our solution is going to be the alpha 1 equal to minus b divided by 2a. Okay, so from here, what we actually do is that we have to use the reduction of order. If we assume that, so if y1 is equal to e to the power alpha 1x is a solution, then by the reduction of order, and this is actually one of the similar examples that we had to look at previously, especially example 5.3.2. So we saw that, well, if e to the power 2x is a solution of this differential equation, then by using the reduction of order formula, we would see that, well, we would actually get x, have an x on the outside as one of the solutions here. So that means if we were to apply the reduction of order formula, we would have y2, which is equal to e alpha 1x times the integral of e to the power 2 alpha 1x divided by e to the power 2 alpha 1x as well, dx. Well, here, then we would see that, well, the integral inside is just going to be your x e alpha 1x. That is your second solution. And so that means our solution to the differential equation, if we have alpha 1 and alpha 2 being real and equal roots, we would have that, well, y is C1 E M1x or alpha 1x plus C2x E alpha 2 or alpha 1x as well, because they're going to be the same roots. Okay, so the last case is if alpha 1 and alpha 2 are distinct but complex roots. So that means what we would actually have is that, well, our alpha 1 and alpha 2 are going to be written in the form of a plus ib, or let me use different variables since I've used a and b already. So let's say we have u plus ib, and that means the other solution is going to be u minus ib, which is the conjugate. So we're going to assume that, well, u and v are going to be greater than 0. And here we know that the I squared is equal to -1. So that means our solution is going to be given by y1, or y, is equal to c1 e to the power of u plus ib x plus c2 e u minus iv x. And that's by the quadratic formula. So if this is complex here, you would obviously get an I. And if you were to write this as a plus ib form, you would actually have these solutions as a plus ib form. Okay, so let us use Euler's formula here. Or in a bit, let me expand this first. So if I could rewrite this as C1 e to the power of ux, and e here, ivx, plus C2 EUX e to the power of negative ivx. So that means by Euler's formula, if you remember, so Euler's formula is given by ei theta is cos theta plus I sine theta. And so from here, if we were to make the substitution, well, instead of theta, we would have Vx and negative Vx here. So here, Ivx cos Vx plus I sine Vx, and E minus Ivx is cos of negative Vx plus I sine negative Vx. But since cosine is an even function and sine is an odd function, we're actually able to write the second part as cos Vx minus I sine Vx. All right. So now if we add the two equations, or combine the two equations, if we make the substitution back into the solution, y here is equal to C1 EUX, multiply that by, so E IVX is going to be given by cos Vx plus I sine Vx. Then we would have plus C2 EUX, and then we would have the cos Vx minus I sine Vx. And here, well, I'm going to be expanding things a little bit. So let's say, well, here, C1, I'll keep the e to the power ux factored. So that means I would have C1 cos Vx plus C1, so IC1 sine Vx plus C2 cos Vx plus IC2 or minus IC2 sine Vx. And so that means if I were to rewrite this, Ux, I could write this as, well, C1 plus C2 cos Vx plus IC1 minus IC2 sine Vx. And all we just had to do here, since we have two constants here, C1 plus C2 and IC1 minus IC2, those are just going to be your arbitrary constants. So we could just set another variable to them and we are good. So let's say we let A cos Vx plus B sine Vx. And indeed, that is the solution of the differential equation. So we went from this differential equation here all the way to this differential equation here. Now, that means we could automatically skip to this solution, which is y's. And so that would be the solution, and be good. Okay, so let's have a look at some examples here. So let's say we want to solve the differential equation given by, so the first one is going to be 2y double prime minus 5y prime minus 3y equal to 0. If you're comfortable with factoring, well, our auxiliary equation is going to be given by 2m squared minus 5m minus 3 equal to 0. So if we factor this, we would get 2m plus 1 by m minus 3 equal to 0. And so that means our solutions of the auxiliary equation is going to be m equal to negative 1/2 and m2 is equal to 3. So that means our solution of the differential equation will then just be y equal to c1 e negative 1/2 x plus c2 e 3x. Nothing too bad here. Okay, let's have a look at the second one. Well, here we have y double prime minus 10y prime plus 25y. So our auxiliary equation will just be given by m squared minus 10m plus 25m, or 25. And if we were to solve this, we see that, well, this is just going to be a perfect square. Set this equal to 0. So that means our one solution is just going to be m is equal to 5. So remember that when our roots are going to be the same, we have to use the reduction of order, which we have luckily found here in case 2. So we could just automatically put here the x e alpha 1x. So that means our m here is going to be the 5. So that means our solution of the differential equation is just going to be y is equal to c1 e5x plus c2x e5x. And that's the solution of the second one. Okay, for the third one, we have y double prime, this should be y double prime, plus 4y prime plus 7y equal to 0. Now, if we solve this by using the quadratic formula, so that means, well, our auxiliary equation, that is, we would have negative 4 plus or minus root 4 squared, or that should be 4 squared, minus 4 times 1 times 7 divided by 2, negative 4. So that's 16 minus 28. Is it? Yeah. Sorry. So this should actually be 12, my bad. So that's plus or minus root 12, which I could actually write this as 2 root 3 divided by 2. And so that means we would just get negative 2 plus or minus root 3. times I here. So I. So from here, we could also make the note that, well, since our u is going to be the -2 and our v is going to be the √3, then that means we could just go ahead and write this as our the regular formula that we have put here. So u is going to be -2, v is going to be 3, or √3. So that means our solution is, so e to the power -2x times a cos √3x plus b sine √3x. And that is the solution. So I'll leave the last one as an exercise for you to try as well, which involves an initial value problem here. But if you find the solution of the differential equation, then you could find the values of a and b if they're real or complex, and you should be good from here. So that is going to wrap things up in this video. So that's all we're going to talk about for the differential equations topic. So our next chapter that we'll actually be having a look at is going to be the parametric equations as well as some polar coordinates as well. So that's going to be for the next lesson, which I will hopefully get that out soon. And yeah, if you have any questions about the differential equations, just feel free to let me know in the comments down below. But without any hesitation, I will end this video here. So have a good day.